Welcome to Sarfatti Science Seminar's Cortona 2023 event. It's May 25th, and today's speakers are Dr. Giovanni Modanese on the interaction between macroscopic quantum systems and gravity, Larry Lemke on exotic fibers and UFOs, and Dr. David Chester on the quantitative analogy between crystal defects in condensed matter to gravitation. I'm your moderator, Tim Ventura, and we'll begin with a discussion of the interaction between macroscopic quantum systems and gravity by Giovanni Modanese.
Okay, so the topic is so kind of summary of a lot of research work done about interaction between macroscopic quantum systems and gravity. And mainly by macroscopic quantum systems, we mean superconductors. But it could also be superfluids. Any system which is macroscopic but has to be described by quantum gravity. So I have been working on this matter for almost 50 years. So quite a long time, but most of the experimental activity, which I will tell you about, stopped years ago. Most of that about 10 years ago. So I must say, in the last years, I've been less motivated to continue my work of phenomenological analysis, of theoretical analysis, theoretical modeling. This research is not currently supported by my university. And theoretical modeling of this sort of phenomena is really difficult. The work I did in particular is based on, the theoretical work is based on quantum gravity, which is in itself a very difficult theory. So it's a hard work, and there has not been much progress in the few last years, except for some recent progress made by my colleagues Antonio Gallerati and Giovanni Marino. I will tell you about this. They have a theoretical model which is basically semi-classical because it is based on general relativity, not in the quantum version, but the classical version of general relativity, plus the Ginzburg-Landau equations, which are used to describe superconductors. So I will tell you about, but also I have to say the model by Gallerati and Umarino has now reached its limits, and it is hard to compare the model with experiments because the effects predicted by the model are on a very short time scale. That's a key point, a key limitation of this model. So I wrote with Gallerati and Umarino a review article for the journal Frontiers of Physics in 2022. And I would say this article is like the history of a long effort by many people. There are maybe 200 citations of research works in the paper. So it was a big effort about interactions between gravity and superconductors. I can say it is not just some sort of fringe science, someone calls this kind of things, but I think it is not. This is just one of those labels used by people who want to have the role of censors, okay, of new physics. And of course, I disagree. This is just a worthwhile research effort. You can see here the front page of the article. This is a mainstream journal. Gallerati and Umarino work in the Politecnico di Torino, which is one of the largest universities in Italy. And the paper is open access, so you can download it. And also in the following, when I mention some paper cited in this review, I will just say the author and the year, but then you can find here all the references. So the paper starts with some historical remarks. The first ideas about spatial interactions between gravity and superconductors, these ideas go back to the 1960s in the work of De Witt, of Papini, Anandan, Chiao. By the way, Papini was one of the contributors, not directly to this review, but to a special issue of the journal Frontiers, which has the same title. You see, it is the title of this special issue is Interaction between Macroscopic Quantum Systems and Gravity, and so there were some articles in this special issue. One was the review, but then we had articles from Inan, who is a collaborator of Professor Chiao in California. Then we had articles by Martin Teimer and collaborator. I will tell you about experiments by Teimer. And one article by Papini himself, and then our review article. Okay, just to mention, there is the special issue of Frontiers, and in this special issue, the review. I was about to say, yes, the first ideas go back to the 60s. And at first, it was mainly about the possible use of superconductors as sensitive detectors for the gravitational field, which is certainly a possibility. But more in general, the question is the description of the interaction of gravity and superconductors through the Einstein equations plus a certain energy momentum tensor correct? From the theoretical point of view, this is the key question, because you see we have here the usual Einstein equations with the quantities involving the gravitational field. We have the Ricci tensor, the metric tensor, the scalar curvature, the cosmological constant, the usual machinery of general relativity, which makes possible to find the geometry of the space as a function of a source. And the source is the T tensor, the energy momentum of matter and of all the fields. And being this gravitational force, normally what matters is only the energy momentum of the sources. So the particular state of the sources is not important in this context. It does not make a difference in the Einstein equations if the source of a field is incoherent matter or if it is a superconductor with a large degree of coherence. So there is no role of quantum coherence in the Einstein equations normally. then I will see, I will show, in my opinion, the role of quantum coherence when you look at the quantum version of these equations comes into the cosmological term. Also, I have to say, all these in connection with the question of the microscopic mechanism of gravity, which is still not well known, because we do not yet have a good theory of quantum gravity. So we do not know how gravity works at the microscopic level. And also, this is one of the reasons why we cannot say what is the role of quantum coherence in a source of the gravitational field. Okay, but in this talk, I will mainly speak about the experimental results. So if we go back to the 1980s, there had been some claims about anomalies in gravitation. For example, there was the story of the fifth force. There were many works about this. It was supposed to be a modification of the gravitational force in a sub-millimeter range. So there were many experiments and theories. And in the end, the outcome was not clear. Anywhere there was a lot of debate. There was another important paper published in Physical Review Letters. This is cited in our article, in our review. If you want to see the details, it was about the possible weight change of rotating gyroscopes. This is also something which is in part predicted by general relativity, but it should be very, very small and not detectable in the laboratory. So there were claims of observations of such weight changes in the laboratory, and then there were confutations. So again, some debate. Then in the 90s came the first experiment by Podkletnov, which I'm going to describe in some detail. And after that, claims about weight anomalies at the superconducting transition. So small changes in the weight of superconductors when they went through the superconducting transitions. As you most probably know, the experiments by Podkletnov have modified at the time the scenario of the research, but until now they are not confirmed and they have not been disproved. So there is a sort of stalemate in this matter. And my opinion, if we want to exit from this stalemate, we would need a sort of large research effort, because the experiments are complex. The theoretical modeling is complex. It would take really some effort from some big lab in some mainstream university or research institution to really say a final word about this. So the superconductor involved in the experiments by Podkletnov was IBCO. This is superconductor with high critical temperature. It is composed mainly of yttrium, barium, copper and hydrogen. That's the origin of the name. The critical temperature is about 93 degrees Kelvin. IBCO brought a revolution in the industry of superconductors because it can be cooled with liquid nitrogen. It can be manufactured in films or in small disc sintered, which means like compressed dust, small particles compressed, forming small discs. And Podkletnov was very smart in his laboratory at fabricating IBCO. He made, I think for the first time, very large discs up to 27 centimeters in diameter. And also not just sintered discs, but discs with a complex crystal structure. And also he used to cool them down, not just with nitrogen, but with liquid helium, so much below the critical temperature. The first experiment, I'm going to call it the first experiment, is the one with rotating and levitating discs. The first version was published in 1992 and the second version in 1997. And then when I speak of second experiment, it means an experiment which is quite different, because it is still with IBCO, but in this case, IBCO is like an electrode for producing high voltage discharges. And these second experiments began in 2002. So speaking of the first experiment with the rotating and levitating disc, the first version was published in 92 in a journal of superconductivity, Physica C. And the co-author was Nieminen. And Podkletnov was working with Nieminen at the Tampere University in Finland at that time, because he came from Russia, but he had settled in Tampere, and formally he was a PhD student, although he already was a professor in Russia. But then he came to Finland and started over with this, let's say, role of PhD student. In practice, he was doing this experiment. And in this experiment, there was one disk which was levitated magnetically, not with direct current, but with low frequency AC current. And the disk was a single layer and sintered. So quite simple in some sense compared to the disk that he used later. There was a radio frequency which was used to irradiate the disk. And the disk was also rotated to several thousands revolutions per minute using additional magnets. So there was a levitation magnets and there were rotation magnets. You could ask what was the original purpose of this device. According to Podkletnov, it was to test the material. So he had no idea at the beginning of possible gravitational effects. He just wanted to test the material under certain conditions. But then he noticed that some small test masses placed above the disk in what he called the region of weak shielding. These masses appear to lose about less than 0.1% of their weight. So he spoke from the beginning of a weak shielding effect, so no claims of total gravitational shielding, okay. I have here a scan of the article. You see, it was entitled "The Possibility of Gravitational Force Shielding." Yes, a possibility, and then he gave these numbers. So 0.05 to 0.3% of weight loss, depending on the rotation speed of the superconducting disk. And you see the two authors in the affiliation here. There is one single picture with the, so where you can see the device. The balance was quite sensitive, of course. There was no big isolation between the disk and the samples, because here you see it was only a plastic film separating the disk from the environment. In the next version, then he placed everything inside a metal cryostat, because there were many objections, of course, about airflow and all sorts of possible errors. Here you can see there was a bath of liquid helium, the supporting magnets, and the rotating magnets. So there was a lot of criticism because theoretically this is impossible. I mean, there is, according to general relativity, no possibility of shielding the gravitational field, not even to this very small extent. The second version of the experiment was published. Actually, it was not published in 1997. So after 5 years, it was accepted in the Journal of Physics D, which is a British journal, and but then it was withdrawn after a strong controversy with the Tampere University. So Tampere University practically, how can we say, they declared they had nothing to do with Podkletnov. Podkletnov was working in their laboratories without any authorization, because the matter was very controversial. It was immediately picked up by the journals, gravitational shielding, and so as you can imagine, after a while, Podkletnov decided to withdraw the paper. The paper was posted at the Los Alamos archive. So we have this version, and actually, if you have a look, and at the time it was called the Los Alamos Archive. Now it is called the Archive, and it is operated by the Cornell University and not by Los Alamos anymore. But it is the same thing. If you look I was actually the one who submitted the paper, but the author is Eugene Podkletnov. I was just helping, let's say, in preparing the paper and formatting. And also I discussed with him some parts about the possible error sources. So it is here, and we can quickly have a look at the pictures. So in this case, the structure of the disk was more complex, and here it is described the fabrication method. I will tell you more in a moment. So with an oven, because the upper part of the disk was melted, and then it got a special crystal structure. And then there are some illustrations of the systems of the rotating magnets and the supporting magnets. Everything was enclosed in a metal cryostat. So details about the rotation solenoids. And okay, this is about the data collection. The cryogenic system. And the method for measurements of weight of the samples. So you see in this case, these samples were hanging into a glass cylinder, and so there was a good separation between the disk and the samples. So the diameter of the disk, the external diameter of the disk was 27 centimeters, and it was more like a ring. We can say it had structure with two layers. At the beginning, there was a sintering of the entire disk, and then it was followed by a melt texturing of the upper layer. That's a known process in which the material, which is melt, then acquires a crystal structure, which is typical of the so-called melt-grow process. And so in the end, the upper temperature, the upper critical temperature, the critical temperature of the upper layer was the usual temperature for IPCO, 94 Kelvin, and with a high critical current. So the upper part of the disk was able to support 15 ampere of current by square centimeter, which is so something you can obtain in very good samples of IPCO. And the lower layer had a critical temperature, which in principle was below the operation temperature. So in practice, the lower layer was not superconducting at the operation temperature. The weight loss observed was of 0.3 to 0.5%. It was measured with several different materials. And in the paper, there is a detailed discussion of possible sources of error. So then came replication attempts. One was done at the University of Alabama in Huntsville in collaboration with NASA Marshall Flight Space Center in 1999 by a group with the leader of the group was Brantley, and then it included Ning Lee and others. And so the detailed story is another review, in another review paper I will tell you about. So in short, they fabricated, so the replication was certainly not complete because they worked in a short time. They first fabricated several single-layer superconducting disks. Then they hired Podkletnov as a consultant, and Podkletnov fabricated a disk with 2 layers. But in the end, the tests which were reported in the publications were only limited static tests. So it means without levitation, without rotation, and not with the disks that had been fabricated by Podkletnov, but just with commercial single-layer disks. So for all these reasons, the replication was certainly not complete. And that there were no weight modifications observed. Also, no weight modification observed by Woods and others in the UK. In this case, the disk was quite small, up to 3 inches in diameter. And also, in this case, many conditions were not reproduced, including the structure of the disk and the levitation and rotation system. Because I would say in these replication attempts, the idea was, if Podkletnov has seen something with his device, but this something is very unusual, because any weight modification isn't to be considered as anomalous. So maybe we can see a small effect with a similar device, which is not exactly the same. I'm not sure this is a good strategy, because this is a complicated experiment, and either you reach the conditions which are in some sense necessary to trigger the effect, or most probably you won't see anything. In the same line is the replication attempt of Hathaway and others. This is a private lab in Canada. They came closer to Podkletnov setup, but only with mechanical rotation, not magnetic rotation, lower velocity. They had lower temperature. They had a gravitometer to measure possible weight changes. And the gravitometer is supposed to be very sensitive, but it is different. For example, it has a very big test mass. Anyway, no weight modifications were observed down to the sensitivity of the gravitometer. Now, there has been a lot of thinking about these experiments. Why are they not working? Is there a chance that so the effect exists, but it is not detected by this kind of experiments? And for example, there is a discussion by Robertson, which is quite interesting, about the experiment by Hathaway. And Robertson thinks in terms of a lack of power input, which may be key for the missing effect. Because the effector needs some power input. It is not just other kinds of shielding. It is sort of active generation of a counterfield, according to some theoretical interpretations. So if you're not supplying power, you're not going to obtain this. Now, this was just a short summary. If you want to read the complete story of these replications, there is this ebook, which maybe you know, Gravity Superconductors, Interactions, Theory and Experiment. It was published by Bentham in 2012, and I was the editor together with Glenn Robertson. And there are 12 chapters in this ebook. The first chapter is just about an historical background with a description of these experiments and replication attempts. And so many more contents. Maybe I can just show them quickly. There is one chapter about interactions between superconductors and high-frequency gravitational waves. 2 chapters, actually. Then there is this theoretical interpretation by Robertson of the experiments. Then there is a chapter with my first attempt of a theory, of a quantum gravity theory, which could possibly explain the effects. Then there are chapters about the timer experiments, the Kiao experiments I'm going to talk about now. Then there is a chapter by Podkletnov and me about an attempt of measuring the speed of the gravity impulses observed in the experiment with the discharges. Then a description of the replication attempt of the impulse gravity generator experiment, the experiment with the discharges. And a chapter by Hathaway and Rice about experiments with weight changes at the superconducting transitions. And finally, 2 more theoretical chapters by 2 German physicists and another one by Robertson. This ebook, if you don't have it, you can write me and I will send you a link for downloading it. Okay, for downloading a personal copy. It is now 10 years old, but it was all about this story of gravity superconductors interaction. Now, the next set of experiments that follow was about transient weight modifications at a superconducting transition. And the first one in this direction was done by John Schnurer, who we could say was an American inventor with a small private lab. And what he observed was that I can show you a picture, then it is more clear. So, you know, you can put a disk, for example, a superconducting disk, you can pin it in levitation above a magnet. So this is the superconducting IPCO. This is a magnet. If you place the disk in levitation, it will stay, and it is actually like captured. It is pinned in a certain position. And now the disk, of course, has been previously put into nitrogen in order to get superconducting. Then if all this that you see in the picture is in air, it will remain superconducting only for a few minutes, and then it will slowly fall down on the magnet. And Schnurrer, this is Schnurrer, observed that while the disk was falling down on the magnet after a few seconds in air, if you placed a balance with some test masses and with a proper insulation. In this picture, the insulation is not very good, but there is some insulation. So you could observe some changes in the measurement of the balance. Of course, you have to be very careful about magnetic materials, because down here you have a magnet, you have a superconductor. At the moment of the transition, there is a big change in the magnetic field all around. So you have to be very careful and use materials which are not affected by magnetic field. Anyway, this was the idea. And Schnurrer made many measurements, about 400 runs, and only about 10% of the runs were positive, in the sense that some weight modification was observed. This was the first experiment. Then there were replications. First replication was done by a group in the Polytechnic of Turin in 1999. Binello was actually a student who made a master thesis about this and observed smaller changes than declared by Schnurrer. So about 10 to minus 3 or 10 to minus 4 of the gravitational acceleration. This was the change observed. I can show you. So the first page of this master thesis. So Binello was the student, but the professors, the supervisors, were all professors from the Politecnico. So at the time, the idea was taken seriously, and there was a seminar in Turin, and Pokletnov was invited. Several professors were present to this seminar. I was present, and Hathaway was present, the Canadian engineer. So it was a time of, let's say, excitement about all this story. Then came results from Rice in Germany. He was working at the University of Würzburg and in the corporate research of ABB, German-French corporation. he observed some weight changes of samples of sintered IPCO. So not a change of weight in some targets, like in the case of Schnurrer. Okay, so Schnurrer had targets essentially made of glass, and similar for Binello. Rice was weighing the entire IPCO while it was going through the transition, so while it was heating up. And of course, this brought errors due to the evaporation of nitrogen, because IPCO was wet and then nitrogen was evaporating. There was a change of weight due to the evaporation of nitrogen. But Rice was an expert researcher just in this field of phenomena of phase transition, so thermal phenomenon in general. So it was a serious work. And also about this work, there was a long controversy. This work was later criticized by Timar. Timar repeated the measurements without nitrogen, and then Rice and Hathaway again repeated the experiment with nitrogen, and so there was a discussion between them and Timar. Here you can see a detail of the experiment by Binello in Torino. I saw it in chapter 10 of the ebook. There is a discussion of all this matter by Hathaway and Rice. Okay, and then after 2000 came the second Pokletnov experiment, and experiments by Kiao in California, Timar in Vienna, and Poher in France. So Pokletnov for this experiment went back to Moscow in labs which were probably former chemistry labs. And so in these labs, he was before moving to Tampere. So he still had there some friends, some collaborators. And he managed to build a big low pressure chamber for high voltage discharges up to 2000 kilovolts of voltage. So very high, quite dangerous. First with a Van der Graaf generator and then with a Marx generator. The chamber was quite large. And there was a superconducting cathode from which he was able to generate a discharge. Let me show a picture. Okay, this is a picture taken from another paper. This is not the original paper, just a simplified picture. You can see the discharge chamber here with low pressure. And there was a liquid helium reservoir for cooling. This is the emitter, the superconductor. And these are lateral magnets to act on the discharge. There are also two magnets here in order to generate a magnetic field on the emitter, which is made of IPCO. And then we had the Mach generator generating the voltage. And what Pokletnov observed was a sort of, let me call it radiation, which was exerting a force, a repulsive force on targets placed far away, up to 150 meters distance, according to his description. So there was like pendulums. He observed some small deflection of the pendulums. So in this case, we had a sort of repulsive field in horizontal direction. And also the direction of the discharge was horizontal because the discharge started from the emitter and went to a positive electrode on the other end of the chamber. This experiment was called the impulse gravity generator. And so it was measured that the total energy of the beam, of the radiation beam generated was not large, about 1 millijoule, but the corresponding momentum was large. So normally, if you have, for instance, a laser or a beam of normal radiation, you have that the momentum carried by the beam is just equal to the energy of the beam divided by the velocity of light. So the momentum is very small in compared to the energy carried by the beam. In this case, it appeared that this ratio between energy and momentum was very different. So it could not be a sort of normal radiation. And clearly this called for a possible reinterpretation of the rotating disk experiments in terms of a vertical repulsive field generated. So what I mean, after this experiment, some people started to think that in the rotating disk, there was actually not a kind of shielding of the gravitational field, but an emission of a weak repulsive field in vertical, possibly in one direction and also in the opposite direction, but not observed in the opposite direction. So in the light of the new experiment, it is also possible to interpret the old experiment in this way. Now, I don't know if I have time to describe all the experiments by Kiao and Taiba. So what I could mention here is that I participated personally for 5 years to a replication attempt of this impulse gravity generator experiment. So this experiment with the high voltage discharges by Pokletnov. There was a replication attempt with reduced size in a private institute belonging to a German foundation called the Gravitation Forschung Foundation. This is in Germany, not far away from Frankfurt. And so for 5 years, I worked not full time, so I made frequent visits there. And the researcher who was working full time was Timo Juncker, and plus some technical staff. there were huge challenges because we had to reproduce the high voltage, the low pressure needed, the low temperature, all the special materials described by Podkletnov. We had frequent contacts with Podkletnov. We went to visit him in Tampere, and so the story would be quite long. We had to build a high voltage cabin for safety because if you make this kind of experiment, I mean, not in Russia, but in Germany or in the Western countries, you have to comply with a lot of safety requirements. We had to get a commercial Marx generator, while Podkletnov had a custom-built Marx generator, very powerful. So it really was a challenge, but the results still were inconclusive. Yes, there is an entire chapter in the ebook by Bentham, in my book with Bentham, written by Timo Juncker, with a full description of all the replication and a lot of details. So, and then there was a replication attempt by Timar. This was also inconclusive, but actually it was at really low voltage and room pressure. So the setup was quite different from Podkletnov's setup. Okay, here you see in chapter 9 the article by Timo Juncker with the description of the replication attempt. So now, very quickly, the experiment by Kiao was about the possible conversion of electromagnetic waves into gravitational waves. And he found an upper limit which was quite small. So the efficiency, if there is such a process, the efficiency is quite small. And Timar made experiments with rotating superconductors. And he claimed to observe some very large gravitomagnetic field generated by rotating superconductors. He made many versions of these experiments. And at some point, he claimed that he was observing a field which, first of all, was very clear because the difference from a null result was 11 sigma, so very clear compared to the noise. But it was very, very surprising because this kind of gravitomagnetic field, according to general relativity, would be equivalent to one generated by a very massive object like a white dwarf star. In 2011, these results were essentially withdrawn, attributing the anomalous effects to some kind of acoustic noise. So this was really surprising also because Timar for years was present in the media telling about his experiments, and then all of a sudden he said no, it was all acoustic noise. Anyway, Timar is still active. He has also made a contribution to I showed you contribution to our special issue in Frontiers. So I think my time is over.
Wonderful. Well, yeah, it's 10:03. So why don't I do this? I think Larry Lemke has a presentation next. So why don't I stop your screen share, Giovanni, and thank you so much for presenting.
Thank you for inviting me. Okay, I stop sharing.
Yeah, I think we're all set. And let me see. Jack, sorry, let me enable it. You can unmute yourself. There you go, Jack.
Okay, can you hear me?
Yeah.
Okay, so I was, I'd actually be more interested here to see you talk about your theory rather than the experiments, but the one thing you did say that the momentum of that beam was bigger than the energy. Of course, that's a space-like interval. I mean, that corresponds to, I would call it, in high energy physics, they talk about the space-like photon scattering. And what you have there is a near field space-like graviton beam, right? Because it's off mass shell, because E squared should be P squared, if it's on mass shell. And so it's like a near field. I would describe it as a near field virtual graviton.
Yes, exactly. You're right.
Yeah, and so that's interesting. And by the way, there is a paper now. There's a paper by Matt Viss's group, came out about a year ago, I think, called Tractor, Pressor, Stressor Gravity Beams, and they have the theory, which I think would apply to this experiment. And the only problem, of course, is that it's the energy problem. That G over C to the 4 is too small to get a big effect, but obviously that's not the case in the technology we see with these machines with the U.S. Navy close encounters. But I want to say something else. But okay. So everything you say about superconductors at cryogenic, those are equilibrium systems. What I am suggesting is that all this can be done at room temperature. Well, we're using the further condensate. And now what the further condensate is, it's basically the laser. But what is a laser? A laser is with photons, but with the laser, the photons, the coherent beam can get out into empty space. This is a laser, what Froelich actually did, the laser is a non-equilibrium system. You're working with thermodynamic equilibrium superconductors, okay? But the laser, you pump the system, and
okay.
in condensed matter, you have quasi-particles. So the idea is when you pump some condensed matter system, an interacting many particle system, you get these emergent quasi-particles, which are non-equilibrium. There's a lot of literature now on emergent quasi-particles in non-equilibrium pump systems. I think they call them flow-quay systems, that you don't see them in equilibrium. You don't see them at thermodynamics. There's a new class of elementary, of normal modes of the system that only emerge because they're being pumped by this external, energy source. And so then you get macroscopic coherence, off diagonal long range order, just like in a superfluid, a superconductor. And then everything you want to do, we can do it much easier, especially you don't have to worry about superconducting. And we know that the machines, the flying saucers we see going around, they're not at low temperature. They're operating at ambient temperatures in the air. So I think that's I think there should be a new, if we had the funding, I think there should be a new series of experiments. First of all, you have to get for the condensates, like in the metamaterials, you have to excite room temperature condensates, and then use your theories, like with the cosmological constant. I wish if we have time, if you could talk about the theoretical stuff that you've done. I'm a theoretical physicist, so the experiments, I don't know, I can't, that's great, but I can't judge the experiments. I'm not an experimental guy. But so I think we could do it at room temperature with the further condensates, and I think that's what we're seeing in the actual operational technology, that there are further condensates room temperature, non-equilibrium pumped. You have to activate the system, and that's the key to understanding what the U.S. Navy is actually encountering. All right, I'll stop there. I think I've rambled on.
Thank you. Very interesting suggestion.
Wonderful.
Larry, going to talk?
Yeah, so I think Larry, Larry is here. Larry, do you want to give it a try?
Yeah, I guess you can hear me now, right?
Yeah.
Okay,
Screen
yeah,
share.
let me share screen.
Just hit the little green thing. There you go.
Okay.
There you go.
I guess you should all be able to see that.
Yes. Yeah, we're good.
Okay.
Perfect. Looks wonderful.
Should I start?
Yeah, go for it. And I'm going to
Okay,
mute everybody out again, and I'll mute myself, and just whenever you're ready.
Okay. And by the way, I'm recovering from a cold. So if I have to take time out to cough and sneeze and so forth, I hope you'll understand. Okay, so this is basically a companion piece to the presentation I made yesterday. And originally I was thinking maybe I would try to include both of them in the same talk, but I don't think I could have crammed it all into a single hour. So it's actually probably better that that it was split up like that. But yesterday we talked about the foil, the so-called Roswell memory foil, and in this talk I'm going to introduce new data, which I actually think has probably not been discussed in public before, regarding fibers that I think also have exotic properties. This is called angel hair, which is not to be confused with the term that is often seen in the classic UFO literature, meaning a fibrous material that sometimes appears in the vicinity of UFO sightings, and oftentimes, falls down and persists for some period of time and then evaporates. This is a different use of that term, so please don't be confused. And actually, this comes out of the story that's told in the recent book by Jacques Belley and Paula Harris, Trinity. So this is material that's related to that story, but has never been told, was not told in the story in exactly this form. And as I said, I think this is probably the first public airing of this. So just to briefly recap, a little town of San Antonio, New Mexico, August 16th, 1945. Excuse me. Or I would say nearby that town, which also happens to be about roughly 25 miles away from the Trinity site, which was the location for the first testing of the atomic bomb, which of course at that time was still highly classified and secret. At that particular time, most of the adult men of the U.S. population were away, contributing to the war effort in some form or another, either in uniform or working in defense industry or whatever. And so a lot of the labor that was needed on the home front was actually taken care of by children and underage, the underage, population that was not off to war. So in this case, Jose Padilla, who was basically the primary witness, was out helping out on the family's cattle ranch together with his friend Reme Baca, and on this particular day. And they were basically being young cowboys. They were riding along the fences to keep the fences repaired, locating all the cattle, rescuing any cattle that were in distress or something. And so they're basically just being cowboys. And near the middle of the day, they both were sheltering from a rainstorm and heard a crash, a very loud crash that seemed to originate from about a half a mile away from where they were. And so they turned to look in that direction, and they could see smoke rising from what appeared to be the impact site or the origin of that crash. So they saddled up their horses and rode over to that site, and they discovered that it was there was a damaged radio beacon tower at the site, and a small field of debris that was scattered near the base of it, and the sagebrush and small trees were on fire, and that was the source of the smoke. And when they arrived at the site and started searching, they noticed a large amount of a white, wispy sort of fibrous material that was scattered in the brush and kind of sticking to the leaves, and in some cases being blown by the wind. They then went on to investigate the location where the bulk of the craft or the object had ended up, and within a day or two, they returned to the site with some large cloth sacks and collected as much of this material as they could, and took it home with them. And eventually, within their family lore, this material came to be called angel hair. And as I said, the more complete story is in the Trinity book by Vallée and Harris. So again, here are sort of the main characteristics that were reported. They were reported as thin, silky fibers, roughly the diameter of a human hair, which I will note in passing is actually quite a bit larger than a typical fiberglass fiber. The fiberglass fibers that are commonly used to reinforce plastics are basically gain most of their strength the smaller they are, the smaller in diameter, and so a fiber that's roughly the diameter of a human hair is probably larger than would be needed for fiber reinforcement of plastics or that kind of application. The fibers would not tangle, even though you could have a bunch of them together. They would not cross or tangle or anything. And again, to me, that kind of suggested that, well, maybe they have some force system of forces on the surfaces that prevent them from wanting to touch each other. One of the more striking characteristics was that the fibers were described as basically self-luminescent. At this particular time and in this particular location, this family lived basically in an adobe building, literally adobe block building with no indoor plumbing and no electricity and no running water. They basically were not connected to the grid at that time and that location. So basically, whenever you went into a room, unless the window was opened or it was daylight, the rooms were dark most of the time. The light that these gave off was described as by both witnesses was very beautiful, like colors of the rainbow. Again, as with the Roswell memory foil, the fibers at one time or another were suggested to high heat to see if they could melt or burn or whatever. Because this occurred on what was basically an operational cattle ranch, they had a maintenance shop located there, which they used to keep things repaired, and so they had access to an oxyacetylene torch, and Jose himself attempted to melt it or otherwise alter it, and could not do so. So it has that in common with the so-called memory foil. The other interesting characteristic that I have never seen reported anywhere else in the UFO literature is the claim that when the fibers would come in very close contact with the skin, like holding it in your palm, it caused pain. It caused a sensation of pain, which was described as something like the pins and needles effect that you get when maybe your hand goes to sleep and it's waking up, and you get that pins and needles effect, and also described it as like a pinch. And they both described it as it would occur when you held it in close proximity to your skin, but as soon as you took it away, the sensation would also go away. So it was entirely transient and not in any way permanently damaging. Okay, well, what happened to the angel hair? And I guess let me just point out here off to the side. Well, let me go with the text first. So initially, as I said, they had collected several bags of this material, and they hid it away because initially, within the first days and weeks after this event, the U.S. military was on the site and was searching their property, searching their houses, looking for anything that might have been related to this incident, that they would take away. They just like in the Roswell case, they wanted to remove any evidence that might indicate that something unusual had happened. But as time went by and the incident kind of faded in the past, they eventually started taking this material out and sharing it with family, friends, neighbors, people who live nearby, and basically it's just sort of the natural curiosity. What is this stuff? We don't know what it is, and so they would just kind of start sharing it. And interestingly enough, it ended up becoming utilized as Christmas orientation, which because it glowed and because it was very beautiful, and so it was used as, you know, for window decorations or Christmas tree decorations. And there is actually, I looked into the sort of the history of that, and industrial processes for producing glass fiber in industrial quantities goes back actually to the late 1800s, and by the 1920s and 30s, it could be produced in routinely in large, you know, industrial quantities. And just prior to World War II, it was starting to be used for the fiber reinforcement of structural plastics, with what today we call fiberglass, and was actually used in the war effort for in aircraft and ships and things like that. In Germany, they actually had a tradition of utilizing this stuff for Christmas decorations from before World War II. And here's a picture of you can still buy some of this stuff on eBay that was manufactured back in the old days. In German, it was called Fienhaar, which I guess means like fairy hair or perhaps angel hair, and oops, excuse me, and this photo is from the 1950s, I think, and probably in the U.S. Shows this kind of material being used as Christmas decorations. And I was born in 1947, and I can remember by the time I was about 5 years old, we were using this material in my household for Christmas decorations, and so I can remember it, you know, very distinctly. The interesting thing is that during World War II in the U.S., I believe all of the production of glass fiber was taken and used for the war effort. I don't believe there was any. I don't believe any of it made its way into the civilian consumer world. And so in the U.S., it wasn't until some years after the war, in the 1950s, that this material became popular for use as Christmas decorations. So in the U.S., it really, you know, from the 1950s onward is when this became popular, and eventually it stopped being used because, of course, raw fiberglass you know, generates small shards very easily and gets, you know, stuck in your skin and becomes an irritant and so forth. But nevertheless, I can distinctly remember having this around probably in the early 1950s. Okay, so so what happened to it? Well, over time, as I said, much of it was given to neighbors and friends and so forth, and never came back. Was never accounted for. The bulk of it that was retained by Jose Padilla and his family was eventually lost in a house fire. The family house later caught on fire. This was not the adobe house, but this was a wood framed house. Caught on fire, and basically everything was lost. So there doesn't seem to be any obvious way to trace any of this today to the New Mexico site. However, a small sample of it was retained by the niece of Jose, and she took it with her when she moved to the Los Angeles, California area. And because she had actually played with it as a child. And but again, over the years, that sample was eventually misplaced and cannot be accounted for today. So all of the obvious paths for trying to track this down seem to lead into a dead end right now. However, both Jose and his niece, Jose, testified to me personally. I've talked to him many times, visited him many times, that he did in fact test it with this acetylene torch, and both Jose and his niece testified to this self-luminosity and to this so-called pinch effect. Okay, so of all that, of all those characteristics, I got interested first in this whole characteristic of self-luminance and all these beautiful colors of the rainbow, and what is that all about? So after thinking about it, I considered sort of the obvious explanations, like perhaps it was radioactive and it was, stimulating phosphorescence or fluorescence or something like that. But those light sources have narrow frequency bands because they're basically, you're elevating an electron in an atom somewhere to some excited state, and it reverts back to the ground state, and it will emit light of a specific frequency, and it's a discrete color. If you've ever looked at a your classic old cathode ray tube, that's what you see. It's a characteristic color. So that did not seem to explain the sort of rainbow effect. And so when you think about a rainbow, in my opinion, I sort of immediately jumped to black body radiation, which has a components of all different wavelengths. So with that in mind, I looked at whether or not I could interrogate these witnesses with some kind of line of questioning that would reveal some of the physics of what might be going on here. And so I started digging into the human perception of color, ranges of color. And not that I'm an expert in this, but here's sort of the basic story. And I assume you can see the cursor here, right? Everybody, the arrow. Okay, so over here we have this graphic here represents essentially the power spectral distribution of black body radiation as a function of temperature, and these are the classic black body curves, and what you see is that for different temperatures, at higher and higher temperatures, the distribution becomes more and more peaked, and the peak will actually shift in wavelength as a function of the temperature. Also, of course, the total power output goes like t to the fourth, and so the total power output also is going to increase as the temperature gets hotter. This little rectangular region here represents the portion of the wavelength of the spectrum that is accessible to the human eye. So anything within this band, your eye could see, and what you notice is that as the temperature rises, the amount of power in any particular wavelength, starts shifting to the left, and so as the intensity of the black body radiation gets higher and higher at higher temperatures, it shifts from the red more toward the blue end of the spectrum. Over here, we have a representation of the response function of the human eye, and basically there are three bands because there are three different kind of receptors in the eye, and each one has its own response function, and each one, you know, peaks at likewise at a different wavelength, a different frequency. So for the human perception of color, or of a range of colors, you have to basically convolve the power spectral distribution of the source that's emitting, and then you have to convolve that with the transfer function of the receptor, of the eye in this case, and then you're able to compute for any given temperature, let's say, you can compute what the mix of colors would be that the human eye would perceive for that case, and that's captured in this lower graphic here, which is called a Planckian locus. And the way this works is that as the temperature gets hotter and hotter, as the color temperature, the source gets hotter and hotter, you move along this line, and the range of colors that the human eye would perceive is basically indicated by this line that's perpendicular to this locus, and so that represents kind of the mix of colors that one would perceive for any particular given, you know, black body radiation. So the experiment that I did was to take both witnesses and show them one of these Planckian loci and ask them to locate the location on this curve that best represented the colors that they were seeing. And I did this independently. I approached each one of the witnesses independently, actually over a period of about a year and a half. And so this one is where Jose put the dot, and you can see that it's somewhere between 5,000 Kelvin and 6,000 Kelvin color temperature, probably a little bit closer to the 6,000. And here's what Jose's niece indicated. You can see also it's basically on the 6,000 Kelvin line, and by the way, there's a lot of variability in each human for the range that you can see, but the sort of the bottom line here is that they both independently located the color temperature as being around 6,000 Kelvin. They didn't know that that's what they were doing because I didn't explain any of this to them. And by the way, neither witness knows what black body radiation is. They don't know what the human eye response curves are, and they don't know what a Planckian locus is. They basically just put a dot on the curve that showed that represented sort of the best fit to what they recall, the colors that they recall seeing. So they both independently converged on essentially the same color temperature of the source. So as I said, in my opinion, the possibility that the witnesses were making this up or somehow getting together, you know, to get their stories together, seems to me to be extremely remote. I just don't see how they would even have the information to get their stories together, even if they wanted to. So that's one element of this story that gives me a fair amount of confidence in this. Okay, so if we assume that set of observations is accurate, what's the explanation? Obviously, you know, the internal temperature of the angel hair was not at 6,000 Kelvin. So basically, there had to be some alteration of the, if it is in fact black body radiation that's been blue shifted. I mean, that would be the answer. That is, it's, you know, black body radiation would give you the color distribution, and if it was blue shifted, that would make it appear to be a lot hotter than it was. So where have we heard that before? Well, from Jack, obviously. So, and the other thing is, so if we did in fact have this repulsive anti-gravitating field on the fibers, again, that would also explain this extreme temperature resistance. So both the acetylene torch test and the color temperature seem to be explained by this. And then I should also mention that in the story, Jose and his niece also testify to having played with small samples of the memory foil that was recovered from the crash. In particular, the niece, you know, described it as you could fold it up like origami and then, you know, put it on the table and it would, you know, spontaneously unfold. So I'm kind of down to my last slide. I do see that there's a hand up. How about if I just finish this slide and then we can just go into the Q&A and we can talk about any of it. Okay, so the bottom line out of this story is that there, if you believe this, there were two crashes separated in time and space. One in 1945 in San Antonio, New Mexico, and another one 2 years later in at Cortona, New Mexico. There are two. Each case seems to have at least one example of thin materials that appear to show this a range of anti-gravitating field on their surfaces. So the two cases are linked by the description of the memory foil, but and so that appears in both cases. However, the one case, the new case, well, it occurred in 1945, but new to the literature, introduces this idea of the foil, of the fibers, which also seems to share, you know, a common technology. And I guess that's the pattern that I'm seeing here, is that the memory foil had these interesting and exotic characteristics, and up until this point, it was seen as a sort of a single event case. But if you accept the 1945 case as well, we now see that it's actually a specific example of a more general technology, which also includes, you know, perhaps fibers as well. So and so I guess the question that I want to leave with, which I was hoping to get discussion on, is that the foil and the fiber both seem to operate as if there was negative mass matter engineered into the normal matter. It's, you know, it's the Bondi pair thing, right? The question is this qualitatively different than the large scale space-time engineering that's needed, you know, to move these craft around, where you're able to actually, you know, create a repulsive field in the front, and, you know, an attractive one in the other side, and you can change the orientation, you can make it, you know, more intense or less intense, control its direction, and so on. So that's required for the large scale, you know, Alcubierre type motion. Is that qualitatively different than this small scale effect, which seems to be unitary in its direction? It's not. It doesn't seem to be, you know, positive on one side, negative on the other. It doesn't seem to vary in intensity with time. It's just built in, like, you know, an electret or something like that. So, okay, so that's basically all I've got as prepared material. So let's go into the Q&A.
Awesome. Larry, thank you so much.
Sure.
So let me do this. I'm going to allow participants to unmute themselves. Let me go to Michael Perrone first, and let me stop your screen share as well.
Okay.
Thanks, Tim. Thanks, Tim. So I was this reminded me a lot about a book my grandfather used to have on the nuclear airplane project. I mean, I think that was disallowed by the Geneva Convention. So Tim, I don't know if you want to remove this from the, you know, edit this out later, maybe, I don't know. So in that book, I recall seeing that they had talked about using thorium oxide fibers to get high surface area for interaction between the nuclear material and the airflow in order to make a nuclear airplane engine. And it sounds like it's possible that if they ever did actually get around to testing that, which they wouldn't have admitted in the book, I imagine, then it's possible some of those fibers flew out the back of the engine, and that's what was recovered. If engineered properly, it would have been a very strong alpha emitter for a period of time, and that would explain the luminescence and the pain in the hands, because
But it doesn't explain the it doesn't explain it all. That I don't believe that. I think what can you guys hear me? Am I unmuted?
Yeah.
I think well, this is astounding. See, I didn't know this. This is first. I know you had this surprise for me. You're my Eddington. Larry Lemke is Jack's Eddington. Yeah. Yeah, I agree with your analysis. By the way, it's pretty funny. This is did Jacques Vallée discover this? Is this Paola Harris, Jacques Vallée, that apparently that Jacques apparently answered that journalist that on the hit piece, right?
Yes, he did.
Yeah, I think Jacques answered that well. Well, this is very important. John, is John Ramirez here? John, can you hear us? Can John? I mean, John really has to spread the word on this. Where's John? John, can you hear?
Yeah, I hear you.
Yeah, John, this is very, very important.
Yeah, I know. I actually was at a conference where both Jacques Vallée and Paola Harris presented on this back in, actually it was back in 2021.
Yeah, but
the
they
book
see
first
Jacques,
came out.
okay, you got to understand something. Jacques Vallée and Paola, I know Paola.
Yeah, I do too. Yeah.
Paola. But then they don't understand physics. I mean, Jacques knows, some physics. Jacques does not understand this kind of physics.
Yeah, and I don't think he did. I don't think he did any of the analysis on it. I mean, I think he.
No, this is
no. I've done all the analysis.
Right.
This is all Larry's work.
Yeah.
I work with Jacques and Paola,
Right.
And I was introduced to these witnesses, and when they started describing, the phenomena that were going on, I'm the one who sort of tried to put together the physics story.
Okay,
So,
Larry, we
Okay.
should write a paper. Now,
Yeah.
we should write a paper now, and maybe Creon could help us. We should write a paper on this, at least for the archive. This is important. Now, this is experimental. Okay, what I'm claiming is that these fibers are part of, they're part of the fuselage. By the way, what happened to the craft? Yeah, how
Well,
come they no
according to the
fibers?
story, it was hauled away by the army to the
Oh,
White
there
Sands.
was a craft.
To
That
the
was
White
okay.
Sands, yeah.
Okay, well,
Yeah.
this is part
Keep
of
in
the,
mind, by the way, that this would have been in August of 45
yeah,
when the Manhattan Project was still
yes.
going on, right?
Yeah,
And
of course.
so my belief is that this material would have been actually given to the Manhattan Project
Yes.
because they obviously were the ones that had the brain power to try and figure out what the hell was happening, right?
Larry, if I could ask, this sounds very much like what Corso described.
Oh, yeah.
Well, that's an interesting question. I mean, he described, optical fibers. I could not tell from his description whether that would correspond to what these witnesses were saying. Because
Well, Corso was not a scientist. Corso was,
Yeah. But I mean, an optical fiber would have been unique in that time period, but it has different properties. I mean, you wouldn't necessarily hang it on your Christmas tree, but I don't know. I mean, I guess I just leave that as an open question because I don't really know enough about what Corso was describing.
right. But we have to write some kind of a paper about this.
Okay, but go ahead.
May I?
Yeah, Creon, please go for it, sir.
Thanks. I'm not really dressed very well, so I have the camera off. Hope that's okay. See, still in bath.
Oh, you look wonderful. You look wonderful. Look at that.
You look like you got one of those beanies on your head with.
Yeah, I got a propeller head.
Yeah, see, I have a flying
do
saucer head.
do some gravity shielding, or some. Anyway, look. Two things. First thing is there was a fellow, I don't know what happened to him, who was talking about nuclear airplanes. I that we could take this offline. I don't think that adds up. Oh, Michael, yeah, right. So we could talk about this offline. It's a side point. What I was going to say, Larry, there's something I don't understand about your claim, and it is maybe I missed it, but it's the following. Black body radiation doesn't look like all the colors of the rainbow. Black body radiation looks like, it looks like, roughly speaking, like if you take a bar of iron and you stick it and you heat it up and it gets hotter and hotter and hotter, it gets red hot, orange hot, yellow hot, white hot. That's what black body radiation looks like in the human eye. It doesn't look like all the colors of the rainbow,
Well,
like diffraction grading, or that requires some kind of spatial or temporal inhomogeneity, or
But that could be in the
and I
crystal,
believe-
can't it?
yeah, and I believe, I mean, I'm not an expert on this either, but I believe that that's what's supplied by the spatial distribution of the receptors in your eye, the three different colors of the receptors in your eye.
Nope.
Hmm?
No, that would imply that if you look at a star, let's ignore the twinkling for the moment, which is from the atmosphere. That would imply that if you look at a star, which is basically a black body, that you would see a rainbow of different colors, because that point dances around on different parts of your retina, and you don't. So, no.
My theory is variable refractive indices due to metamictization of the thorium oxide, but that's a whole other.
Yeah, right. Well, look, if you're gonna now invoke additional properties of this material that causes it to have dispersion or diffraction in some way, yeah, right. If you put white light onto a diffraction grating or through a prism or through even generally lenses, it separates into colors, and you can see that. But if you just heat something up as a black body, it kind of doesn't even matter how small it is. It doesn't look like the colors of the
But you
rainbow.
could have both things. I mean, this is presumably a very complicated kind of small scale structure that none of these
Sure,
people saw.
sure, and we can speculate about what those things are, but I mean, even like fiberglass and stuff like that, if the fibers are parallel, particularly starts to make rainbow effects because
Yeah.
of the diffraction grading. I mean, it'll make rainbow effects.
Yeah,
out in
so
the
it's
sun.
not necessarily a zero-sum game there. You could have, but it could be what Larry says, the blue shift.
Yeah.
And it could also
No, it can't be the blue shift. That's my point. If you blue shift the black body spectrum, you still get an approximate black body spectrum. It doesn't look like
true. Yeah, but wait. I agree. But if there's inhomogeneities and anisotropies in the small scale structure of these angel hair fibers, it could act also like a prism as well as
Yeah, fair enough, Jack. But my point, I'm not trying to knock down Larry's whole theory.
Yeah, no, I understand. That's a valid
Let me
point.
just
Yeah.
let me just say, capsulize it. Just having black body emission, redshift
won't explain it.
not at all from a
Yeah.
fiber is not going to look like the red colors of the rainbow. You got to have.
No, it has to be this other structure, some kind of prism like micro prism.
Well, what about the fact that if these are in fact round fibers, and you look at one, different rays from different rays are going to come off at different angles, from the
Yeah.
fiber. And I wonder if now you're starting to get something like the the rainbow effect that occurs from water, suspended water droplets in clouds.
Right.
Yeah, right. And now you're just invoking, say, the dispersion of the fiber, the refractive index of the fiber. So you could just hold it in the sunlight and presumably get the same kind of effect. Yeah, and I mean,
except that this seemed to be self-luminous, right?
yeah, okay, fair enough. But I just want to say that that
No, okay, that's a valid point.
that's all. I've said it. Thank
Yeah,
you.
okay, I get it. Yeah, thank you.
Listen, we should all get together when I'm back in San Francisco, when you're up in San Francisco, Creon, you, me and Larry, and see if we can, produce something.
Come up with a consistent story. Yeah.
I'm
You
more
know,
interested-
if I could mention with self-luminosity, one of the things I was looking at was day glow for something else, but what interested me was that it basically downshifts ultraviolet right into the visible spectrum, and so potentially maybe the self-luminosity. I mean, obviously you could look at something like radioactive materials, but potentially maybe it's something as simple as downshifting UV from the environment into the visible spectrum.
Mhm. Well, no, see, I think
otherwise known as fluorescence.
Fluorescence.
I don't know if there's enough UV to do that realistically.
it would seem to me that that's not consistent with the fact with the conjecture of it being a repulsive field, an anti-gravitating field, right?
Exactly.
That's going to blue shift it, and presumably what it would do is it would blue shift whatever the native temperature of the fiber is, which in this case I would assume is in radiative equilibrium with the surrounding, not
Exactly.
convective, but
Exactly.
radiative. And so it would normally be like in the thermal IR.
There's something
But
else
shifted
that,
upward, Huh?
did any of them get sick?
No. No. And the other thing that I really would like to talk to Kit Green or somebody about is, or maybe Gary, I guess, is this whole thing about the pain or the pinch that was felt. Again, to me, I think you could explain that as a short range field, which is basically able to essentially alter the flow of neural pulses in the nerves. I think I would view it as sort of direct neural stimulation of the sensors in the dermis, in the epidermis.
Mhm.
But I don't know.
Okay, well, this is certainly interesting. Now what's happening next?
Yeah. So let me go back to my list. Actually, you guys wrapped up commentary right on time. So let me see. David
Oh.
Chester, quantitative analogy between crystal defects and condensed matter due to gravitation.
Oh, good. Yeah. Oh, there's the Hagen climate. And by the way, De Hooft, apparently Gerardus De Hooft is into this too. He knows Hagen climate.
Nice.
Well, David, if you'd like to start, I can mute everybody out again. And
All right. Yeah, sure. Let me share
Sure.
my screen.
okay, well, thank you, sir.
Start the slideshow. Hopefully everyone can hear me all right. See. All right. Everyone can see the first slide okay? Should be good. All right, sweet. So today I'm going to talk pretty fast because I have too many slides. I had 200 that I cut down to about 97. So I'm going to talk about a quantitative analogy between gravitation and condensed matter and discuss work towards a more general theory of relativity. Thanks for inviting me to this talk. I appreciate it. So we're interested in gravity and condensed matter because we want to use condensed matter to create metric engineering. So we're going to need collaboration between gravitational theorists and condensed matter experimentalists. So to accomplish this goal, we're going to need to find some sort of common language because we're dealing with different subfields of physics. So in this talk, I'm going to propose that we should push the gravitational theorists into the language of condensed matter because the theorists have more mathematical complexity, so they should be able to handle this transition better than going the other way. So another motivation for why we might want to do this is because we're most likely going to need to do numerical approximations at some point. If we're going to be simulating these materials before creating them in a lab, it's probably going to be difficult to find exact solutions. So that motivates approximations such as discretization schemes or Reggie calculus, for instance. So in this talk, we're going to be thinking about this analogy between space-time and materials. So we can quite literally think of atoms of space-time, and we're going to think of taking the limit as the atoms go to 0 in size to go back into the continuum. But by the end of the talk, we're going to view everything in the discrete realm. So we can think of modeling flat Minkowski space-time as a crystal, and then realize gravitational fluctuations as defects, world crystal defects away from the crystal, such that arbitrary curved manifolds would have a collection of defects throughout. And another point that will be common throughout this talk is that there's many ways to express the low energy dynamics of general relativity, and we don't know yet what the best high energy theory of gravity is. So we need to keep this in mind as we go into the laboratory, because if we're seeing anomalous effects that may or may not agree with general relativity, I mean, we're also interested in trying to understand how nature is fundamentally described. But at the same time, we don't want to be too heretical, and we want to respect Einstein's legacy. So just to think about this, we can reflect on how electrodynamics has advanced over the past 150 years. So we know that Maxwell's equations are valid at low energies, and we know that we have the theory of quantum electrodynamics, which Dirac helped with. And we know that at high energies that Maxwell's equations break down. So if we go above the Schwinger limit, we get this Born-Infeld electrodynamics where the photon itself becomes nonlinear. And this is, you can actually derive this theory as the one loop renormalization of QED. So this is just an example where we know that QED respects Maxwell's legacy, but at the same time, we know that the gauge theoretic properties of quantum electrodynamics help us go beyond Maxwell's theory. So we want to think about, maybe we can learn from history from this example and apply that to gravity. But first, we might want to think a little bit more about what a gauge theory is. So Dirac himself had some ideas on how to formalize gauge symmetry, and he looked at these Hamiltonian constraints. For instance, it's very common to go to the Lorentz gauge in electromagnetism, and that localizes the electromagnetic fields. And there's also, in linearized gravity, there's this de Donder gauge, which is very similar. So if you take h mu nu as the fluctuation around some background metric, and you take the trace reversed metric, you can subtract 1/2 eta mu nu times the trace h. If you take the partial derivative of that and set it equal to 0, that's known as the Dodonder gauge or the harmonic gauge. There's about 10 other names for this gauge. And so that is called a gauge choice in some sense. But in the modern day, general relativity is not a gauge theory in the same sense that electromagnetism or Yang-Mills theory is. So there's a little bit of confusion or tension because Dirac obviously is an excellent figure in physics, and he had his views on what gauge symmetry is, but his views differ from the modern conception. So when I say gauge gravity, what I'm actually referring to is a formulation that really Ivanov and Niederle, this paper from 1981 clarifies what I mean. But in Yang-Mills theory or electrodynamics, we have some Minkowski background that has Poincare symmetry. But then there's this separate structure with some gauge group G that has some gauge symmetry. So for QCD, it might be SU3. For electromagnetism, it might be U1. But that SU3 or that U1 has nothing to do with Minkowski spacetime. It's completely independent. So when I talk about gauge gravity in this talk, what I mean is that similar to having some Minkowski spacetime, okay, that gets updated to some curved manifold. And instead of having Poincare symmetry, there might be diffeomorphism invariance. But there's still this separate structure that has some gauge symmetry, G. And at least in the formulation that they discussed, this gauge symmetry would always contain the Lorentz group and sometimes the Poincare group, or maybe even the conformal group. So here it's different than what Dirac was thinking. We have this base manifold and then some other local structure, let's say, and there's actually maybe a frame field that goes between the two. And so while GR only had this manifold, gauge gravity adds this additional gauge symmetry. So in these gauge theories, we often have this notion of transport or derivatives, and so we'll have these covariant derivatives. So if you had Yang-Mills theory, let's just say you had SU3 and you had 3 quarks, and so you had some spinor field, and just forget about the spinor indices. Let's say you had I running from 1 to 3 for red, green, and blue, and then you're gonna, in the matrix formulation, you could get 8 gluons as a gauge field, and then contract that with the structure or the generators, and then you could get some matrix formulation of your Yang-Mills gauge boson as a connection. And in gravity, it's very similar, especially in gauge gravity. You can think of this as being, you could think of it as being a spin connection, or you could use global indices as well. So the connection, the affine connection in gravity is very similar to a Yang-Mills gauge boson. So that is very helpful to keep in mind. So just to provide some additional motivation for studying gauge gravity, it's worth mentioning that supergravity and string theory, they're all studying gauge gravity. Loop quantum gravity is studying gauge gravity. Poincare gauge gravity is a formulation that's gauge gravity theory. I'll talk today a lot about this metric affine gravity theory, which can be formulated as a gauge theory. Geometric algebra is claimed to be a completely other different route. They often end up in the gauge theory. And general relativity itself can be modeled as a broken gauge theory. So there's some motivation. And so you can have different Lie algebras or Lie groups that can be used for these gauge theories. And as I was mentioning, the Lorentz group is one of the most common. So SO31 is used for the Lorentz group that describes rotations of space-time. And for spinors, we might take a double cover to get to the spin group. So when we take, say, fermions and put it in curved space-time, it's very common to study Einstein-Cartan theory, which actually is a gauge theory of gravity that uses the Einstein-Hilbert action, but gauges the Lorentz group. Or you might have heard of Ashtaker variables that also is using some gauge group. There's you could use spin 3,2 to get to ADS gauge gravity. You could add some supersymmetry, or you could study the conformal group with spin 4,2, which is the same thing as SU22. So there's conformal gauge gravity, and you could make it super conformal. Also just mention that Yang in 1974 discussed gauging the general linear group with Yang-Mills theory. So that's worthwhile to mention. And also AL4R is the affine linear group that adds translations to the general linear group, and that is the gauge group for metric affine gauge gravity. So I'll motivate that a little bit more. So basically, we might want to think now, okay, so if we're trying to respect Einstein and Dirac's legacies, how can we do that? How can we go beyond GR yet still respect what both Einstein and Dirac said? Well, if we think about it, Einstein really did discover the importance of diffeomorphism variance, and Dirac was smart to point out that in some sense, you can say that the diffeomorphism sort of looks like a local gauge symmetry in a way. So why don't we consider a theory of gravity that gauges the diffeomorphism group such that it could limit to GR at low energies? Now, if we wanted to do this, it's actually very challenging, and it's not even clear to me if the mathematics exists to do that, but conceptually, we can at least talk about what this might look like. And so if we were to gauge the diffeomorphism group, my idea is that this would be almost like there's some fictitious fluid. And we know that in the theory of elasticity, that when an elastic medium is just a fluid with small displacement. So, you can have a table, it's not going to be fluid, but you can deform it a little bit with just very small displacements. And so we expect that if we just gauged linear diffeomorphism transformations, then that would just correspond to small displacements. So if we go into this high energy gauge theory and we just only consider the gauge transformations associated with the linear gauge aspect, then we're going to get some finite dimensional gauge group, and it's going to give us an elastic medium rather than a fluid. And this is actually what metric affine gravity is claimed to be. So basically, it's also, so in one sense, we can say that metric affine gravity is a low energy limit of this diffeomorphism gauge theory that I can't even develop for you. And then within metric affine gravity, we're going to show how there's actually multiple different ways to recover general relativity, which is why talking about this becomes so difficult. And I'll also mention that the diffeomorphism group does contain the conformal group. So in this sense, we see that it might be possible to consider a gauge theory of gravity that gauges the diffeomorphism group that still respects both Einstein and Dirac's legacy and might give us new physics. But this is a very grandiose picture, so we have to take a lot of care of this. So it's also worth pointing out how the classification of gauge gravity is currently going. As it currently stands, when you look into the literature, I mean, the string theory supergravity community is kind of dominating at least kind of the particle physics high energy theory aspect of physics right now. And they end up, they'll go to GR, they might add some supersymmetry. The highest they get, they might gauge the Poincare group sometimes, they might gauge the conformal group, but they're kind of unaware of this metric affine gravity. They're not very interested in studying metric affine gravity. So in some sense, there's kind of this schism, because in the pure gravity community, they have been exploring this metric affine gravity, but they've also been exploring this conformal gravity. And if you look back historically, it all goes back to Weil, who introduced the scale transformation. And so it's worth pointing out that the scale transformation is contained both in the conformal group and contained in metric affine gravity, but the conformal group contains additional transformations not contained in the affine linear group, and the affine linear group contains additional transformations not contained in the conformal group. So in some sense, we want to also, Hermann Weil invented gauge theory, so people are trying to figure out the best way to use his insights, and there's kind of this breaking point, because you can go the conformal route or the metric affine route. And no one has really concretely showed an explicit theory that would bring them together. But it is known mathematically, there is at least one or two obscure papers that showed that you can actually combine metric affine transformations with conformal group transformations in a nested way to get to the infinite dimensional diffeomorphism group. So in that sense, we might say that, well, general relativity is certainly a general theory, but in some sense, these theories right here are more general, and maybe we could claim that the most general theory would be this diffeomorphism invariant gauge theory of gravity. So that's kind of the language I'm going to be using for this talk. We'll have general relativity and maybe some more general theory. I'm mostly going to talk about this. This most general theory is so deep and advanced, I'm not really going to have much to say about it. So just to give a little bit of background on where I came from, essentially, I was always interested in quantum field theory. So my PhD thesis was looking into methods that could find gravitational solutions, gravitational waves from Yang-Mills theory. So there's this method that my advisor found called the double copy that shows how graviton scattering and radiation, and the radiation is off shell, as Jack has said multiple times, that those solutions to GR can be generated from Yang-Mills theory. So that's a very curious observation for theoretical physics, because we know that Yang-Mills theory is used for the standard model and GR's theory of gravity. So we want to figure out how to bring gravity and a standard model together. And there's this method that seems to relate solutions between the two theories. And it goes deeper than this. There's actually, so Yang-Mills theory is right here and general relativity is right here. So there's this color kinematics duality that allows you to do this double copy to find solutions. But we now actually understand that there's a network of quantum field theories whose solutions are all related. So this network includes many, many, many more theories than this. This is just a small example of it. It includes the Born-Infeld electrodynamics, as I was mentioning. And so there's another duality that can be used there. There's also the nonlinear sigma model. That's the theory of pions, and that's right here. So we can basically take nonlinear sigma model solutions, turn them into Yang-Mills theory, turn them into GR, or we can turn them into Born-Infeld and then into GR. And I should also mention that technically this double copy gets general relativity plus an axion and a dilaton, which is jokingly called n equals 0 supergravity, because it's not a theory with supersymmetry, but string theory is giving us this axion and dilaton. And this double copy has nothing to do with supersymmetry. It works in arbitrary dimensions, and it gives this axion and this dilaton very naturally, just simply because the tensor product of two vectors gives you a matrix, and the graviton is a symmetric matrix. So you also get a trace and an anti-symmetric piece in a matrix, and that trace corresponds to the dilaton, and the anti-symmetric piece corresponds to the axion. So we know that solutions to Yang-Mills theory, which is a successful quantum field theory, that those solutions are related to the graviton solutions in GR plus these axions plus this dilaton. And we also know from history that this theory of pions it gave a nice theory, but it wasn't renormalizable. And we know that historically pions led to, we eventually realized that the weak force is very important for pions. And so once we introduced the standard model, that became the gauge theory that replaced this non-renormalizable theory. And notice how GR, it's a similar story. GR is also non-renormalizable. And you can look at spin-spin interactions and for fermions and see that you can actually get mediation of spin-spin interactions via torsion, which is actually very similar to claiming that it's very similar to W bosons. Before you had Yang-Mills theory and you had pion interactions, you might have some W bosons. The W bosons are analogous with torsion. And it's also well known that Hall-Bremon axions can be found when you integrate out torsion in string theory. So there's this very bizarre point in the community where I was at a conference, and they'll say that everyone acknowledges this, that torsion is the same thing as axions in some sense. It's undeniable. It's just a mathematical fact. Yet it was once stated that, well, torsion's crackpot, so we're only going to look at the axions. So basically, if we're only looking at this particle content and we're neglecting the torsion, we're never going to get to the gauge gravity, because we need to look at the gauge theoretic origins to really see what is going on. And I'll also mention that there's obscure work by Tucker and Dorelli that showed that the dilaton relates to non-metricity. So we know that the graviton relates to curvature. And so this double copy may actually, the origin of this double copy isn't really fully understood yet. And so you may actually argue that gauge gravity could help describe the origin of this double copy with torsion and non-metricity, because we know it's related to the axion and the dilaton. So if we're going into this more general theory of relativity and we're interested in gauge gravity, we should think about what different types of geometry we can have, right? So there's the Riemannian curvature or pseudo-Riemannian curvature that's used in Einstein's general relativity, and we know that's sourced by the stress energy momentum tensor. But then Cartan was looking at angular momentum, and he wanted to find an analogous response for angular momentum, not even quantum spin, just angular momentum, but it is true that quantum spin is an example of angular momentum. And so Cartan mathematically introduced this notion of space-time torsion as a form of geometry. And similarly, Hermann Weyl also introduced this notion of non-metricity, which now gets used in conformal gravity and some explorations of cosmology at times. So metric affine gravity was introduced in the 1970s by 1976 by Friedrich Hell. And this combines curvature, torsion, and non-metricity. So metric affine gravity has all three. And so that's why I'm interested in this metric affine gravity, because it's using the most general geometry in some sense, well, at least more general. And so we can find low energy string theory within metric affine gravity, because we know that we can get this axion and dilaton from torsion and non-metricity. And I just mentioned a few works here. So another theme that we'll talk about is there's this notion of a geometrical trinity of gravity. So I'll just briefly introduce that concept now and state that you can get equivalence to general relativity with curvature, you can get it with torsion or non-metricity. So saying that spin sources torsion is really a convention on how you're setting up the theory. You could also have theories where everything is torsion and there is no curvature whatsoever. So this makes it very difficult to talk about. Now, I'll also mention that there's this theory of quadratic metric affine theories of gravity that was discussed here, which is also a nice paper. So if we're interested in getting at anti-gravity, we're going to have to be very conservative. I'm not really going to talk about any specific proposals. Really, I'm just going to outline some of the mathematics that might help us work towards evaluating if if we see something in a lab one day and we can't make sense of it, it's at least good to be aware of this differential geometry in case it comes in handy. And why I'm saying that should be more clear by the end of the talk, especially if I have time. So I'm going to skip this. Basically, anti-gravity is hard because of the G over C to the fourth. And when I say quantum gravity throughout this talk, I really mean just physics with G, C, and H bar. I mean, at the end of the day, we're going to be using condensed matter, which involves quantum states of matter with H bar, and we're interested in gravity with G and C. So even if you don't believe in quantum gravity at a philosophical level, when I say quantum gravity, I just mean that we're going to have physics with G, C, and H bar in some sense. So that's kind of what I mean. So, but this is really a note to myself. We have to keep it simple. So let's go back to basics and just review some aspects of general relativity. I don't have much time, so I'll just mention that we have space-time vectors, right? And well, technically they're not vectors in the curved manifold, but we have these coordinates on the manifold, and we can measure infinitesimal lengths with the space-time metric g mu nu, which is also known as the graviton in the field theoretic interpretation. So we can then, as I was mentioning before, you can have a covariant derivative, which gives us some connection, which is helpful for describing transport. For instance, we can have a geodesic equation. And also, it's worth pointing out that general relativity is metric compatible, which means that the non-metricity vanishes. And so I'll introduce the definition of non-metricity. It is a 3 tensor that transforms properly as the covariant derivative of the metric tensor. And so in general relativity, the non-metricity tensor vanishes. And that's what we mean when we say it's a metric compatible theory, is that this tensor is 0. And also general relativity is torsion free, which means that the torsion 3 tensor vanishes, which refers to the antisymmetric part of the affine connection. So if we have a metric compatible and torsion free affine connection, we know that that is uniquely determined to be the Levi-Civita connection, which can be found by taking derivatives of the metric. So in general relativity, we have this metric field, and we can find the connection uniquely from the metric. And as I was saying, that describes transport. And once we have the connection, we can then find the curvature tensor. And this is a 4 tensor that transforms properly. From there, we can find a Ricci 2 tensor and the Ricci scalar. And this goes into the Einstein-Hilbert action such that we can find Einstein's field equations as a second-order differential wave equation, because we know that the curvature tensor is a derivative of connection, which is a derivative of metric. So we get two derivatives on the metric in Einstein's field equations. And so we know that the stress energy momentum tensor is what sources gravitation. So if we have some matter Lagrangian, we can vary it with respect to the metric to find the stress energy momentum tensor. But let's think for a second. I mean, even in general relativity, without getting into this gauge gravity business, why are we calling this a stress tensor? Where did this come from? Well, actually, it comes from elasticity theory, right? So, and then you could ask yourself, well, how did this stress tensor get into general relativity? And really, I mean, there's a lot of history that we overlook now, where physicists in the early 1900s were thinking about elasticity theory probably a lot more than we are today. I never took a class on elasticity theory. I had to, read Landau-Lifshitz myself and figure it out. It's actually a pretty complicated theory. It's kind of humbling to look back at the 1820s and see what they were working on. And so, as I was mentioning before, you could have some elastic medium that has small displacements. And so you could measure length. And so you could deform this medium and see how the length changes. And you could look at, basically, you could characterize the difference in the length by some strain tensor here. And so for whatever reason, they like to put a factor 2 here so they could get another factor of 1/2 here. I would have just never put that factor of 2 in there, but hey, that's all good. It cancels out. And so if you look at the strain tensor, it's actually very similar to what sometimes are called local diffeomorphism transformations in GR, especially in linearized gravity. So these displacements are very similar. So if you considered u to be small, then this term right here is quadratic. It's a u squared. So these gauge-like transformations that we see here are actually simpler than what has been discussed in the strain tensor here in the 1820s. So we're dropping some quadratic term here when we're going to these Lie algebras that are linear. So that's why I was mentioning that it's not even clear to me if the mathematics for this, if we were to allow for a fluid model instead of an elastic medium, we're going to have large displacements and we would get even higher order terms. And even these Lie algebras already are dropping terms found in the elastic theory. So it's going to get pretty complicated if we're going to go into the fluid model. So let's just stick to elastic media for today. So Hagen Kleinert is one of my favorite researchers. He's done a lot of interesting things. Feynman could not figure out the path integral for hydrogen. And so he asked Kleinert to think about it. It took him over a decade. He realized that torsion was necessary. He also discovered that real physics, atoms in the real world, molecules have broken supersymmetry. And also he's studied Poincare gauge gravity via this world crystal defect story that I'll talk about. And so it's just kind of curious. So, I mean, recalling that the ether was a material, I'm not saying that Kleinert said this, but I mean, he's literally treating space-time as a material. So it's just kind of curious. So you can see why people might not want to think about these ideas because it sounds too much like an ether. So we're going to get into some of what Kleinert did, but first we're going to have to talk more about metric affine gravity. And it's a very confusing formalism because you're deforming length itself. So it's like your rulers are almost not well defined in some sense, or it's very difficult to wrap your head around how to make sense of any of this stuff, which is why the string theorists don't even want to look at it. So there's a lot of interesting questions you could ask. Now, there's different formulations for looking at, let's say, tangent space, right? You can have a point on a manifold, and then you could look at the velocity on the tangent space. And so it's common to look at a tangent bundle, but you could also have a rolling tangent space and have a tangent manifold with a Cartan geometry. Maybe a way to think about it is these metric affine spaces allow for slipping, so you could have rolling as well, and slipping. And so this ambiguity allows for a lot of gauge redundancy. So it's powerful in some sense, but kind of like a Ferrari, it's very high maintenance. You have to really know your mathematics to get it to work, and it's very confusing to figure out how to work with it appropriately. So I should mention that the affine linear group is taking the general linear group, which are just 4x4 matrix transformations, and then adding the translations. So we could have some matrix transformations here, and then we could add some translations here, and you could embed it in 5 dimensions to think about a 5x5 matrix to implement your translations if you want to look at it that way. And so it's also worthwhile to note that the Poincare group can be found in the affine linear group. The general linear group also has shearing transformations. So if you remove the shearing transformations and the scale transformation from the general linear group, then you just have the Lorentz group, the rotations left over. And so if you remove you can also just remove the translations to get to the general linear group. And then if you remove the scaling and shearing, then you would get to the Lorentz group down here. So we see how the Lorentz group and the Poincare group and the general linear group all fit into this affine linear group, which we could then treat as a gauge symmetry if we want. And so it's understood that that if you gauge the Lorentz group, that relates to curvature. It's well understood that if you gauge the translations, that relates to torsion. And it's hard to find this in the literature. A lot of people are confused about the true gauge theoretic origin of non-metricity, but it's because it's not even a gauge group, it's a quotient space. It's the GL4R modded out by the Lorentz group, which is not a closed group. So if you're just to gauge non-metricity, it's a little funny, it's this quotient space. And so we see that we have 3 different gravitational field strengths in this metric affine gravity, and they contribute 3 different contributions to the affine connection. So if we, our big A will be our gauge field, the affine connection for gauge gravity, and it'll have some Levi-Civita piece, and it'll have some contortion, it's called, and disformation. And I like to formulate it in this way because it's very difficult to remember all these things, but you can actually think of the Levi-Civita connection, you can think of it as actually being a Schouten bracket, it's called. The Schouten bracket of 3 indices gives this configuration of these indices with a plus sign, this term, and then one with a minus. And so if you put the minus sign here and here, you can get it. So the partial derivative of the metric is you just swap that out for torsion or non-metricity, and then you can get the contortion tensor and the disformation tensor, which goes into the affine connection. So we see that we have this Levi-Civita piece, we have a contribution from torsion, and we have a contribution for non-metricity all going into this affine connection. And then from there, it's worth pointing out that at this point, transport becomes ambiguous because there's geodesic transport that only uses the Levi-Civita connection, but now we have this notion of autoparallel transport that includes the full affine connection, which would include the contortion and disformation. So at this point, if you're looking in general relativity, the contortion vanishes, the disformation vanishes. So the autoparallel transport is identical to the geodesic transport. But now, if we're in these metric affine spaces, there's a difference. And so then you have to go into how do you even interpret these things? There's not a consensus in the field on the best interpretation as far as I can tell, but I think the best interpretation is to think about the geodesic path as being the true path that gets taken. But if you follow the geodesic, let's say you had a vector and you transform that vector, if there was torsion around, the vector might twist. And so the geodesic transport would go along the right path, but it wouldn't give you the right twist. And so what you could do to figure out how much it got twisted, you could follow the autoparallel path. The autoparallel would be a different path. It wouldn't have twisting of that vector, but that autoparallel path would start at A and end at B, just as the geodesic would start at A and end at B. And when you follow the autoparallel path, you'd get a final vector that could be different than the final vector of the geodesic path. And that final vector from the autoparallel path would include the twist that would have been found if you follow the geodesic. So in some sense, it seems like what you want is neither the geodesic nor the autoparallel transport. However, you want to almost follow the geodesic and figure out where the vectors go from the autoparallel transport and use both of them to figure out what is going on. As far as I can tell, that is the best interpretation, but there is no consensus, perhaps. And so we'll explore this more, but you can characterize curvature and torsion and non-metricity via holonomy by infinitesimal transport. I'll show examples in a bit, but keep in mind that curvature and torsion are 2 forms, which means that they're defined by transporting around an area, and non-metricity is a 1 form, so it's defined along a line. So in some sense, it seems like curvature and torsion are sort of more bulk, whereas non-metricity is more boundary in some sense, because if you had, you had a square, right, the perimeter is more one-dimensional, whereas the square itself would be two-dimensional. And so non-metricity is fundamentally different than curvature and torsion because it's a one form. And so this is the differential forms language of what I was saying. So this is the Riemann tensor, and now we actually we have these gauge fields. So we have two local indices A and B. Sorry, I deleted the slides that introduced the frame field because I have so many slides. So this is our torsion 2 form with one index left over for the local gauge, gauge coordinates, local coordinates. And then this is a 2 form here, so we get this RAB. And then we see non-metricity is a 1 form. There's 1 curved indices and 2 local indices removed. So in the metric affine gauge theory, we say that we have 3 different gravitational potentials: the spin connection, the frame field, and the metric. And so the spin connection is a 1 form, just like a Yang-Mills field. So you can get some omega mu AB and then a dx mu, which I suppressed. And then there's also this E mu A dx mu as a 1 form. And you might have heard that the metric is a 2 tensor, but here I'm actually treating it as a 0. It's a scalar. It's a local metric, not the global metric. So this is the gauge theoretic metric, GAB. This might be new to you because usually the frame field is pulled back to a flat Minkowski metric, but now it's like we have a frame field, we pull back from the global metric, and then instead of getting to a Minkowski metric, we still have an independent local metric, which is, so we have this metric affine formulation where we're treating the metric and the affine connection independently. So we can't pretend that this is Minkowski because we might have some local non-metricity. All right, and then, so we also get 3 different types of sources in metric affine gravity. And so we have the metric stress tensor, we could call it, which is the typical stress energy momentum tensor in some sense. Yet there's also this canonical energy momentum that varies with respect to the frame field. Sorry, E and theta are kind of used interchangeably here. And then same with gamma and omega, sorry about this. And there's also this hypermomentum. So if you take the connection 1 form and vary with respect to that, you get this hypermomentum, and that is fundamentally new in metric affine gravity. So it's really ironic if you think about it. The stress tensor is found from varying the metric, yet metric affine gravity actually treats the metric as being something new, yet the new source is this hypermomentum, which comes from the connection. So it might actually imply that the way we've been thinking about general relativity, everything's a little turned around, but it's a matter of perspective. So as I was mentioning, holonomy helps define these things. And so the basic idea is if you start at P, you could go from P to Q to R, or you could go from P to S to R, and you could transport this vector. You could go from P to Q and assume that's an infinitesimal distance. Let's say you ended up at some vector here, but when you went this way, you ended up at some vector here. If the 2 vectors end up being rotated from each other, then that means there is curvature. And so you can look at the difference in the 2 vectors, which characterizes how much they're rotated, and that relates to the definition of the Riemann 4 tensor itself. So we have the d mu representing the translation in the x direction, let's say. We have the d nu, let's say we're translating in the y direction. We have this initial vector with a sigma, d sigma, let's say, and then we have this final displacement dx rho. And so we have 4 indices. We have the mu, the nu, the rho, and the sigma. And so this intuitively shows you why the Riemann tensor is a 4 tensor through the lens of holonomy. Basically, if you go around in a circle and come back to where you start and the vector gets rotated, then that means there's curvature. So gauge theoretically, curvature is linked to rotation. On the same footing, torsion is related to translation. We do the same thing, but now we don't have to worry about translating a vector itself. We just consider even a scalar. So we could just transport a scalar field, and we could go from P to Q and then go it up to R, or we could go to P to Q prime. And let's say we applied the same, it's like you go in the X direction and then you go in the Y direction. And then instead you went in the Y direction and the X direction. You'd expect that, you'd come back to the same point, right? If life is simple, you'd expect R and R prime would be identical because I'm just going X then Y versus Y then X, I should end up in the same spot. But if you don't end up at the same spot and there's a translation, between R and R prime, then that translation is a caricature of how much torsion there is. And so torsion in this sense is a notion of infinitesimal non-commutativity. And so that shows you why the torsion tensor is a 3 tensor, because we have, once again, the 2 form representing the area that we walked around. We walked around a loop and saw how much we got translated by, and that amount of translation relates to this rho index here. So torsion relates to the gauge theoretic aspects of energy momentum or space-time translations generated by the energy momentum generator, at least in quantum theory, as how it's typically expressed. Finally, non-metricity is a little different because it's more about transporting 2 vectors along an open line and seeing how their dot product changes. So it's not a 2 form, it's a 1 form. And so I should have written Q mu A B. So we're transporting along a line, but then we have 2 different vectors, let's say A and B, and we could consider how they get sheared or maybe their length changes. And so the scaling and shearing is characterized by non-metricity. It's a very exotic form of differential geometry, way more exotic than torsion. So as I was mentioning, there is this trinity of gravity, and I was noticing this before this paper came out. I was looking at this in 2018. I noticed all the papers that they cited here, and there's general relativity, which has curvature. And you might have heard that Einstein later in life had this teleparallelism that had torsion. You know, what's that about? It turns out that you can make it equivalent to general relativity. And by at least 1998, it was realized you can get a symmetric teleparallel equivalent to general relativity that has non-metricity. And so what I'm saying here is kind of mind-blowing in the sense that you'd think, okay, well, general relativity has curvature, and then everyone's telling me, oh, I need to find the torsion to give me something that's different than GR. But it's worth pointing out that you can use torsion to describe dynamics that are equivalent to GR, and you can use non-metricity for dynamics that are equivalent. So that makes it very difficult to talk about. All right, so I'm going to have to speed this up. And basically, there's this metric teleparallelism with torsion, and because it's metric compatible, so the non-metricity vanishes. And then symmetric teleparallelism has non-metricity because the affine connection is symmetric, which means no torsion. And a parallel theory means the curvature vanishes. So this only has curvature, that only has torsion, this only has non-metricity. And this is the action for it. You can actually find the action by taking the, you take the total non-Riemannian curvature, set it equal to 0, and then you solve for the Riemannian Ricci scalar, and then solve for what is left on the other side of the equation, and then you'll get this. And so you can derive the action just from Einstein-Hilbert in that way. And there we go. And it's actually curious because Einstein thought this was a unified theory, and he studied it, and he thought it also had electromagnetism. Lemke wrote in a letter in 1926, I believe, maybe 28, around that time, that it was only a theory of gravity. So then, you know, Einstein's failed theory of teleparallelism actually is a valid theory of gravity. It just doesn't have electromagnetism. Well, more to say on that. I'll probably run out of time though. So non-metricity, you can do the same trick and get a Lagrangian here for non-metricity in this symmetric teleparallel theory. So don't worry about this too much. So basically the idea is there's this trinity of gravity that's a triangle, and you can find that triangle in this cube. So this cube is, I got scooped basically. I was trying to write a paper on this cube of metric affine gravity, and then they just simplified it and took the triangle. So I just stopped there. So if we have no curvature, no torsion, no non-metricity, we have no gravity. We can think of that as special relativity. We could add some curvature, maybe think of that as general relativity. We could add just torsion, get this metric teleparallelism, or we could add both, right? So you can get Einstein, if this Poincare gauge gravity actually contains curvature and torsion, and it's the Poincare gauge gravity unifies Einstein-Cartan theory and metric teleparallelism, but then the metric affine gravity unifies all of them in some sense. And so this metric affine gravity is very complicated because we see that it contains general relativity in at least 3 different ways. And so that's kind of this deep, profound thing. And there's, once you go to the full metric affine theory, there's other contractions that you can find as well. And so this is that 28 parameter Lagrangian I also mentioned. So as I was mentioning, all of these contain general relativity. It contains Einstein-Hilbert right here. It contains the metric teleparallel, it contains the symmetric teleparallel. So you can imagine going to higher order terms and eventually getting an infinite number of terms. And you can even imagine metric affine level lock gravity as well. And I was taught that string theory disagreed with level lock gravity. And so it's kind of a problem, because how do you predict what all these coefficients are? But it turned out that string theory might actually predict these. There's a paper that claimed that. So maybe string theory is falsifiable and could help us, surprisingly. But that's not, most string theorists wouldn't say that. So just worth pointing out. So finally, we want to kind of get into the defect story with the little time I have left. And we're going to talk about how this ambiguity in defects relates to the ambiguity in differential geometry, which relates to why Einstein was confused, why he couldn't get electromagnetism, and why he rejected Weil's use of non-metricity erroneously. So I'll summarize this again. I got to get going. So we have disclinations as one type of defect. And so the idea is you can have some medium, you cut the medium, you take out a wedge, and then once you take out the wedge, you kind of you glue the medium back together. And so you can imagine taking in the discrete setting, let's just say you had a 5x5 square grid, and you cut out 90 degrees of that and stitch it back together. So it almost looks like the corner of a cube, right? And so now this little patch, you could say, has curvature because it has this wedge disclination. So here's another way to look at it. If you just think graph theoretically, you don't care about the positions of the points. It's just a graph. And so in that sense, graph theory, this is the same graph as this. And so you can see we started with this square thing. We took a wedge out and then we stitched it back together. And so if you started with this initial green vector and you walked around this defect and you kept track of, you pretend this is the X direction, that's the Y direction, you kept those conventions. If you were to walk around this defect, you would see that the final red vector that you end up with gets rotated. So we see that this discrete polynomial is reproducing curvature from the wedge disclination. So that's a good thing. And so there's this ambiguity, as I was mentioning, because we can look at the same defect in two different ways, right? We started with this thing, we took out a wedge, and then we took that blue piece out, we stitched it together, and we said, that is curvature. Aha, I understand what is happening here. But you could interpret the same defect in a different way. Rather than taking out a wedge, you could take out an infinite number of lines, where each of those lines turns out to be a dislocation that corresponds to torsion. And so you can reinterpret the same defect as really a stack of line dislocation defects and refer to it as torsion. And so here's an example of a line defect where we started with a square lattice and we just removed some vertices in a line rather than in a wedge. And so there's also a screw dislocation, which is a little more complicated, but it's kind of like a parking garage structure. So it's like you keep trying to come back to yourself, but you accidentally end up at a higher level. And that's from this type of defect that corresponds to torsion. So you can look at it in the discrete or continuous setting. And so here's another example. And so you could do the same game where you play the holonomy, you apply this line defect, you go around, and since it's like you expected a point to be here, but now there isn't a point. So you went up one step and you went up two steps. So when you come back to where you started, when you're not where you thought you would have been due to the defect. And so you get translated, and that translation due to holonomy is a signature of torsion. And so here's just the simplest possible example on how to compute the torsion from the defect story. So basically you can just figure out how much you get translated by and figure out how that leads to which components of the torsion tensor are non-zero. And there you go. So you can look into the details later if you want. So there's also further ambiguity that I was interested. Kleiner didn't study non-metricity. He only looked at curvature and torsion. So you can also have vacancy and excess defects, zero-dimensional defects. You just add or remove a point. And so you can actually sum over, you can imagine that a line defect is just a sum of point defects. So the same exact story happens again. You can remove a point, you can add a point. We also have the freedom to decide how we want the connectivity to happen, which Kleiner didn't discuss. And so there's ambiguity, right? We have these defects. That the defects seem to be what's actually going on. We have this manifold, we're changing the manifold, but there's different ways to characterize how we think about those defects. And so that has maybe deep implications that I don't have time to talk about. So here's another example, right? Let's just say we started with this patch and we added a point. There's two different ways to interpret the same thing. One thing is to say, hey, all of these edge lengths are unit 1. It was a 2x2 square. From P to Q is length 2. From up here to here is 2, 2, 2. It's all length 2. So when I add this third point at a graph theoretic level, I have the freedom to decide how I interpret the geometry. And so I could say, no, this whole length is length 2, or I could say, no, this length is 1 and now it's 3. So if you say that this is length 3, then you're now saying, when you do the holonomy thing, you're saying it's torsion. But you could also say, no, the calibration of my ruler got deformed. Actually, when I transported this vector along this point, it actually changed length such that this whole side length stays length 2, such that this little length right here is now 2/3 instead of 1. And so it's the same defect, the same thing, but now we're just saying, no, there's no torsion, it's non-metricity. So it's ambiguous. And this is why Einstein's refutation of Weil doesn't make sense, and Schrödinger pointed it out, because in the language of defects, Einstein is saying, hey, energy and momentum and stress sources these 2D wedge disclinations as curvature, but Cartan introduced these line defects, which Einstein eventually used for his teleparallel theory. And then Weil said, well, hey, I want to study electromagnetism as these point defects. And Einstein was saying, hey, but Weil, you can't do that. This non-metricity is too weird. You're deforming lengths, you're muddling everything. It doesn't make any sense. You can't remove points. You can only remove lines. And Schrödinger is kind of saying, well, look at this thing right here. I took away 3 points. Did I remove a line or did I remove 3 points? I mean, it's the same thing. So you can't really introduce torsion and then claim that you can never use non-metricity because they're ambiguous. So basically, this is just summarizing how a wedge disclination can be a sum of edge dislocations, but you can also flip it around. You can actually combine 2 wedge disclinations and have them overlap with opposite charge percent. So if you add a wedge and subtract a wedge and put them infinitesimally different, you can actually make a dislocation that way. So we can go back and forth. We can use the disclination to form dislocations, or we can use the dislocations to form disclinations. And the same thing happens for non-metricity as well. And then if you wanted, you could imagine generating, I guess my point is non-metricity is kind of the most fundamental defect because you can generate all defects by summing over the zero-dimensional defects. So you could integrate over a line from the zero-dimensional defects. So you could imagine some defect generator that acts on a manifold to spit out a new manifold. And just some comments, basically, these tensor vector scalar theories have been studied from 5D theories. And so it's worth mentioning that you can restrict torsion and non-metricity to only have vector pieces or scalar pieces in some cases. I just mentioned this because Jack did briefly have an email that stated this. And so you can look at some of this differential geometry in different ways. Einstein-Cartan theory, it still kept that curvature, but it introduced non-propagating torsion. But it could turn out that we actually want the torsion to propagate. Maybe it turns out there's some spontaneous symmetry breaking going on in gauge gravity that leads to maybe some massive scalar vector field, and maybe torsion and maybe the axion gets some mass, maybe the dilaton gets some mass. So there's a lot of exploration that basically the field is kind of scared to go into because it's complicated. People don't like gauging non-compact gauge groups for whatever reason. They think it has problems, but it's not as problematic as it seems. So supergravity, I mean, we can say string theory isn't that useful, but they have done a lot of interesting work into studying spontaneous symmetry breaking of gravity. They've been more adventurous than other researchers. So maybe their exact theories aren't exactly what we want, but they've implemented a lot of tools that could be helpful for studying maybe like superconducting like aspects of gravitational dynamics could be coming from spontaneous symmetry breaking of gauge gravity. So you could also mention how conformal gravity might lead to another way to get equivalent to GR that has been discussed in literature, and there has been discussion of anti-gravity and conformal gravity, and some interesting connection between the Higgs sector and the dilaton. And once again, string theory and supergravity is predicting anti-gravity for extended supersymmetry. Joel Shirk is the same guy who also discovered that torsion is the axion. I mean, this guy essentially invented string theory and supergravity, so nobody can really say that he's crazy, right? So he's saying, hey, look, you know, these supergravity theories have anti-gravity. That's just a fact. So string theorists might not like to focus on that, but you know, you could have these graviphotons, and you might go into the you know, when you go into the community and you hear these tinkerers talking about, oh, I hate general relativity, you know, it's too complicated, blah, blah, blah. All we need is Maxwell's equations. I mean, I disagree with that, but it is historically interesting to point out that heaviside gravity was the first theory to have gravitational waves. But it turns out that this graviphoton is really just picking GR and adding you know, a Maxwell term, a heaviside gravity term. So you could think of some spin 1 gravitational boson as being like a unification of Einstein's theory and heaviside gravity. That's what's coming out of here. If you just look in that paper, you'll see it. And so metric affine gravity could give some of those dynamics. That 28 parameter Lagrangian that I showed you has multiple different one of those terms, but we don't know the coefficients of those. So it's hard to know. And so, you know, as you're aware, we could have an Alcubierre drive, but we need a large quantity of negative energy. And so there's also been conventional string theorists talking about traversable wormholes. And they claim that these wormholes were negative energy states. So now that you've seen what these defects can do, I mean, if general relativity doesn't have the differential geometry to create a point in space-time, to create a, you know, if you want to create a portal in space-time, it seems like you need to be able to puncture the space-time manifold, open up that puncture and figure out how to connect it to something else. We want to create a wormhole. It might help to understand, at least think about what torsion and non-metricity can do for us, because it'll give us a more granular, a more microscopic way to think about how to engineer space-time. So really metric engineering, to master metric engineering, it seems like non-metricity and torsion might be necessary to get everything, but we might not need it, right? You know, we might just be able to get by with curvature. So in conclusion, basically, we can view gravity in a formulation that treats everything as a world crystal. So we're pretending space-time is like an elastic medium that has defects, and those defects are characterizing the gravitation. At least if we're sticking to the Einstein-Cartan view, where we still have GR and we're just adding torsion, maybe those spin density could source torsion, and maybe charges in electrodynamical theory could source non-metricity. There's also work by Poplavsky showing how that could work out. So we know that black holes have mass, charge, and spin, and we know that there's 3 types of differential geometry, and we know that condensed matter systems that we're interested in, they have charge and spin, right? But astrophysics, they're typically low spin density. I mean, these stars are huge. They're huge. I mean, yes, they're rotating a lot, but the spin density is small. And so a lot of people don't even get to non-metricity, and they look into astrophysics and say, hey, there's no torsion. I'm never going to measure torsion, so why do I need it? It's not for astrophysics. It's for condensed matter. It's for elementary particles. And, you know, similarly, stars don't have net charge typically. It's condensed matter that does. So if we're interested in applying gravitation in the condensed matter laboratory, we should, I think we, you know, hopefully we don't need all this exotic, crazy differential geometry. But if it turns out that someone gets some material that has some exotic properties and we can't figure out how to describe it in terms of curvature, I mean, it might help to just be aware of these things. Maybe it can lead to new forms of anti-gravity. Maybe these defects could eventually help us understand how to do more specific metric engineering. Maybe it help us understand how to do things like wormholes or get negative energy, what appears to be negative energy states. Maybe the idea is that there were some papers saying that this non-Riemannian geometry with torsion and non-metricity could give what appears to be negative energy states. There's still debate on this. So I'll just leave it at that and conclude there and say that this is at least a language that we can use to help facilitate communication between gravity and condensed matter researchers. So thank you.
Amazing. Amazing. David, let me do this. I'm not sure if this is the convention or not. I want to put this on gallery view, and everyone needs to give an enormous hand to David Chester. That just, you blew my mind like 50 times. So
Thank you. I really appreciate it. I'm glad people enjoyed it.
yeah, no, amazing, amazing. Let me go to Jack. He has his hand raised.
Hey, Jack, you want to
so-
unmute? Tim might need to unmute everyone. I'm not sure.
There we go. Yeah, I've got
Okay,
it.
David, first of all, please send a copy of this talk.
Sure.
Yeah, by email, okay? And let me just point out, I actually, one of the reasons Abdus-Salam invited me to Trieste back in 1973 is I had a crazy double copy. I had a paper, double SU3 giving the eightfold way, rather the oath, a double eightfold way, two SU3s giving general relativity. I mean, it was just a stupid, this is back in 1971 or so, 72, maybe 73. Okay.
And
it was
Salam
actually
was
published.
interested in the
It was actually
chromogravity.
published. Herbert Furlick published it in his Collected Phenomena paper journal. But it was, I never really got anywhere with it because I didn't know enough stuff back then, and that was a long time ago. But yeah, I think these extended connections, the torsion nonmetricity may play a role in the metric engineering, inside the metamaterials. So we have to certainly be aware of it. But yeah, but send me a copy of that paper, okay? Of what
Definitely. Yeah, and I will say that for me, the biggest thing is to realize that in GR, we have this metric, we have this connection, and we have this curvature. But in Yang-Mills theory, we just have a connection and a curvature. There is no metric. Oh, wait, but there are Hertz potentials. Hertz potentials, you take a derivative of Hertz potentials, and they give you the electromagnetic potential. And so you could imagine non-abelian Hertz potentials or something like that, and maybe that those structures could help relate to some of the theories that Salam was after, because he was interested in these chromogravity theories. That's probably why Salam was interested in what you're saying. So I didn't get into that, but you can imagine if you're going into unified field theory, you can learn more about gravity and electromagnetism and the strong force. You see that there's pieces on both sides that are missing. And so,
hey, by the way, is
math-
Hagen Kleiner still alive? Are you in touch with him?
I haven't reached out to him ever, but I think he's alive still. Yeah.
Okay, well, maybe we can in this, if we could get some funding for the October meeting, be good to have Hagen Kleiner come, and you come, and Creon Levitt was saying it'd be good for Ray Chow, who I know, to come. But let's see what happens. Okay, so didn't you have something? You had your hand up, Jose? Did you?
Yes, he did.
So I wanted to have some connection of what you discussed with actual cosmological measurements. And for example, there is a recent paper that just came out May of this year that goes over metric affine theory and does some calculations for a black hole as well as for a model of dark energy. So for the black hole, I think it doesn't. I don't know. My question is, I want to have your comments here. I don't know whether you have seen this paper, but for the black hole, it doesn't find anything interesting. It, from my point of view, it finds that it still has a singularity at the center, and there is a singularity due to torsion as well. And as far as the dark energy, it finds that one can have a cosmological constant term that is driven by torsion instead of being something that just enter there, a cosmological constant, and you don't have any explanation for. So do you have any comments on this paper or on other papers that are trying to to
Definitely.
relate it to actual cosmological measurements.
Yeah, definitely. Of course, I don't know exactly what paper you're referring to, but I've seen definitely similar papers. There's a lot of different papers that are going in different directions and taking different interpretations. I'll just say generally, overall, it is true that metric affine gravity or some of these other theories can change the singularity structure of black holes. So torsion can lead to different singularities. Perhaps, I mean, rotating black holes, it seems like eventually when you really think about high energy rotating black holes, you kind of need torsion, it seems. Even when you go into the Penrose-Newman formalism, Penrose essentially forgot that he included torsion in his own work. So the singularity structure of black holes has changed, and it does have implications for cosmology. But I mean, there's so many different ways to recover the cosmological constant. It's hilarious. I mean, it's hard to pick which one is the best, right? Yeah, you can get it from torsion for certain. I mean, basically, anytime you get some type of scalar field in any way, and you can, there's a lot of different types of tricks to get, to sort of freeze it and get a cosmological constant. Magdal-Mansouri gravity gauges the ADS group, which has torsion in a sense, but it doesn't have torsion propagating, but it's kind of like an Einstein-Cartan type of thing, and they're able to get a cosmological constant that way. That goes back to 76. Poplawski also did it in Einstein-Cartan theory, and maybe a decade ago, got dark energy from torsion that way. I also feel like, for some reason, I feel like non-metricity and the scale transformation might suggest, and the relationship of the dilaton to non-metricity, I'm curious if that's really helpful.
Can I have another question?
Yeah, sure.
So you mentioned the dilaton again, which the dilaton also comes, for example, in a scalar tensor theory. But my question is, well, there is no evidence whatsoever for a dilaton. So to me, that the theory has a dilaton is a problem rather than being something good about the theory.
It's hard to say. How about this? How about, let's just talk about the axion. All right, so the axion dilaton are somewhat similar in some sense. Supergravity theories sometimes even put them together into a complex field. So, I mean, one of the most common candidates for dark matter right now are axions. So it is possible that dark matter could be axionic, which also then implies that torsion could play a role. And basically, it could turn out that the spontaneous symmetry breaking of these theories lead to things like massive axions. I'm less sure about the dilaton, if it should be massive or not. There's so many different ways to explore it. So at least we can say, the axion is one of the most common candidates for dark matter. And, just as you're critical about the dilaton, you could be equally critical about the axion. However, I mean, we do know that there seems to be matter in the universe that we don't understand. So it's entirely plausible that the axion and or the dilaton could relate to dark matter at some point. But a lot more research is needed. Sure,
okay.
Sure.
So that to me is another problem, because the action was a possibility maybe a decade ago, but now we have so many measurements that have excluded a huge portion of the window, and there is very little remaining, right?
I don't know how true that is. There's so many, it's crazy. Same with the dilaton, there's so many different axion models. Ask theorists, what's the mass of the axion? You can hear whatever you want. And a lot, as far as I can tell, a lot of the experiments, I mean, I have a friend who published work, or he's trying to get work published. He believes that he knows the exact mass of the axion. I don't know exactly what to think of what he's claiming, but I don't know, I at least have a collaborator that's been looking at this stuff. And a lot of these experiments, they're really, they make it seem like they're rejecting large ranges of the perimeter space, but it seems, as far as I can tell, it seems to be a lot more narrow than it seems. He believes that the axion actually has been experimentally detected, but it's just the interpretation of the detection is not appropriately done. So yeah, I'll just say that there's a lack of a consensus, and
Yeah, if I could jump in there, there's also a lot of phenomena that have been observed, like squeezed vacuum states, which might play a role somewhere around here, but those are, for one reason or another, not considered in our model of particles and things. Spatiotemporal optical vortices as well, stuff like that. So photons with strange orbital angular momentums and stuff like that. All that has to do with entanglement of photons, and it seems to introduce these additional spins and things. But anyway, yeah, go ahead, David.
Well, I
So
mean, it sounds like that's coming from photons, though. Yeah. So I mean, it's like, are there more fundamental fields for gravity, or elementary particles per se, like graviton-like objects? Yeah. I mean, I'm not saying that I would say 100% that these axions and dilitons have to exist. I just think it's at least there. It's hard to know for sure. It's very difficult to make a consensus on these things because it's very complicated.
Yeah, I would say a lot of the things have been ruled out before we really can 100% do that because of some assumptions, for sure.
Okay, listen, what are we, what's happening next? Are we gonna adjourn or are we gonna continue?
Yeah.
I had a few questions as well.
So Jack, I think it's up to you.
Well,
What
how many people are still here? I think people are getting tired.
I think they are getting tired.
Yeah, I think we should adjourn, but listen, I made a very fun presentation, which I'll do tomorrow, but I've already posted it. I've posted up on Twitter. It's my pinned tweet. It's a PowerPoint with the audio, and it's all very intuitive. It's all, I call it all uses Roger Penrose's light cone pictures, where if you're a right brain artist layman using Roger Penrose's pictures, you can get a very good idea of plain vanilla general relativity, not the stuff that David Chester's been talking about. This is just the Levi-Civita, just curvature, the disclination defect, and you can really understand what warp drive is. You can understand why why the high G's that they report for the UFOs, why that's an optical illusion, and you can really understand a lot without any algebra, without any math formulas at all. Feynman had his diagram technique to do quantum electrodynamics and do quantum field theory, to do Yang-Mills, everything that David was talking about is usually done now with these Feynman diagrams. Well, the Roger Penrose's light cone diagrams are analogous for general relativity in space-time, but the Feynman diagrams are in energy momentum space or Fourier transform space. But in any case, it's a fun thing. It's easy. This will be an easy, intuitive way for non-mathematicians to kind of see what's going on, including warp drive. So it's already on Twitter. I think I must have sent most of you email with a link to the Twitter. It's just a PowerPoint. I'll just let it run. And so that's what we'll do tomorrow at the beginning, okay? So that's tomorrow's last session, right?
Wonderful, wonderful. Jack, let me, on behalf of everyone, let me thank you so much for putting on this event. It's an honor to attend.
Okay, and David, please send this paper.
I'll send over right now.
Okay, good. All right. Okay, so we'll see everyone tomorrow then, right? Hopefully.
All right.
Okay.